So first of all, I would like to thank Dusan and the team for organizing this great event. It was an absolute pleasure yesterday with Venkat. Thank you, Dusan, very much, and all who is responsible for this afternoon. I would like to follow up on what Venkat was briefly touched yesterday on some of the technologies that he mentioned, and also on later today on Scala programming language, where we will have around 3 hours long workshop on Scala for Java programmers. My name is Radek Strnad. I'm a system engineer from CAI, which is a vertical AI studio that has also offices here in Košice. You may ask what is vertical AI studio? It is let me give you an example. We are producing startups that rely solely on AI. If you take, for instance, Facebook, they give you a social network, and also they are monetizing their profits from advertisement and information about you. They use ML for hiring up their revenues, but if they don't have the ML, you can still, post on the wall. You can tag yourself in your Axis wedding photos, and you can do all sorts of things there. So, Tower Street is one of the projects where we use AI for recognizing risks on data breaches, and we are insuring companies against these data breaches. We are also, apart from estimating the data breaches, we are trying to estimate the magnitude, the scale of them, the repetition, and also the losses of companies. When we are assessing companies, we of course have data about the companies, what are their weak links. So we know that, yes? Quick time is running. I think so. Yes, it is.
Sorry.
So, when we are assessing the companies, we of course know what are their weak links. We know that if someone is sticking their passwords on the monitor and they are not really paying attention to their credentials, that they are very likely to get their data stolen. So we are trying to work with the companies and tell them, okay, so if you are going to enforce the two-factor authentication, then we will lower the premium on our insurance and it will cost you less. So it is beneficial for both parties. At the moment, we are using for our machine learning model, which is the core of our startup, we are using around 50 company and breach-related data sources that we are linking together. So we are having security ratings from external companies. We are using historical stock information, SEC filings, and breach records that are mandatory in the United States. So whenever anyone is breached, you have to file it, and we are pulling this data from attorney generals, and we are analyzing them and trying to spot some patterns. At the moment, we are only beginning, and we are processing only 70 gigabytes of raw data, out of which 90% are stored in S3 as a static files. We get them periodically. Sometimes we get them once per month, once per quarter, year. These are the reports that we use, and the rest of them we crawl from the web, and we crawl them quite regularly. To be able to build the model, we have to link all the data of the companies and breaches together, and build the model and run Monte Carlo simulations on a large number of cases that will predict us what are the possible losses and what can actually happen to the company. This is a slide where we can see just a brief overview how the data can be crunched. This is a on this axis you can see the frequency, how often the breach can occur, and how many records can be stolen. So naturally, the more breaches, the less data get stolen, but there are some breaches that are very, very dangerous. When we are starting with a startup, we have to, or the first mission we have is we have to validate the hypothesis that we can build an ML model, that we can extract predictions out of it, and we can use it for our business. So in the beginning, we don't know, we have tons of data, but we don't know in advance which attributes will work for the model. So we have to maintain all of them. As I said, we have to link the data between each other. Unfortunately, there isn't a single unique identifier that is appearing on all of our data sources, meaning we don't have a unique ID for a company or breach, so we have to use some native language processing for the data we have for the attributes. So we are using web addresses of companies, the names of companies, and the other attributes by which we link the data together in a quite fuzzy way. We have trained the model for tokenizing and extracting the names of the companies, and by that we link them together. We have a research team that has to access the data in some nice fashion with a query language they are familiar with. So we are using SQL for that, and we are keeping interim results along the way when we are processing the data, so we can easier debug the data, and we can trace back what actually happened in the pipeline if something goes wrong, and it always does. So yeah, we use Postgres to the rescue, because ML people love Postgres. And if everything goes okay, and we link the data correctly, this is what you can see. Well, in late 2013, there was this retail company called Target that at the end of the year, someone stole from their network 41 million of personal records, names, addresses, and credit card numbers. And as you can see, as soon as the news broke out, their stock prices started to follow the pattern of Bitcoin of last week. You know. So when I joined the project, we actually had the proof of concept done by the ML people. And not only ML people love the Postgres, but you can't touch their Python. You know. They use their Jupyter notebooks, and they wrote Python crawlers, Python scrapers. The scrapers are like units that take the raw data and extract and normalize the data so they can be processed for machine learning further. Then we had these Python linkers, which were single-threaded, lovely, and we had to insert and read all the data from and to Postgres. And it was somewhat orchestrated with Airflow, which is a product done by Airbnb, I think. And it took us 7 days of runtime. If nothing, crashed. So, the mission was obvious. We have to push the speed of the processing of the data pipeline to something that is much faster. Also, it has to be more reliable. And the goal we set was under 24 hours. My personal goal was to do it overnight, because when the guys will put in some new models, they want to test something new, they will launch it at the end of the day, and at the beginning of the next working day, they will have their results, and they will be able to assess if it was successful or not. We still had to output to the sacred Postgres, and we told ourselves that we want to run concurrently in different environments. So we can have several data pipelines running alongside. We will just spawn more machines. we want to version the data. We didn't do that in the beginning. So we knew what were the sources, how did the data in between look like, and what was the result. So we had snapshots of the data. And we wanted to plug in the new data sources. Easy. There are some restrictions on how this could be achieved. We had to keep it simple. It's just number one of all the development. Don't over-engineer, never, never, never. You know, do just the minimal that is required for what is your goal, and reuse as many technology as possible. It looks like it is a really, really obvious restriction, but I've seen so many programmers following this one, so I had to stress it out. At the beginning also, I was the only one who was dedicated full-time system engineer, so I couldn't make some technological choices that would include me maintaining some infrastructure. So we had to use some of the technologies that were in cloud, and also the changes had to be performed along the way as an evolution of the data pipeline that was already in place. Because remember, we have a ML team that is working on the ML model, and they have to work. They can't be stopped just by switching to another technology or waiting for me to deliver something that takes a month or 2 months. This is just not acceptable. If you look at the original layout of how the technology looked like, so we had data that got crawled from web and data that were stored in Amazon S3. And we were crawling them with the Python, and we were storing them into Postgres. Then we had some scrapers that were cleaning the data. They read the data from the Postgres, done some magic, and inserted the data back into Postgres. And in the end, we read again all the data in the linkers, and again with these single-threaded Python scripts, we were linking the data together. So, as you can see, this has many, many bottlenecks and many, many fragile parts that can go wrong, and they did several times. We had, first of all, we had long-running crawlers, and long-running crawlers weren't caused as much as downloading a lot of data, but we had some services that you have to pay for, and they give you some speed by which you can download data, or you can download a certain amount of data per day, and then they just tell you, okay, come next time. So we had these long-running crawlers. These were problems, and this couldn't be speeded up just by throwing more machines or more threads or just scaling up. We had dependencies in the pipeline, meaning if one of the crawlers, and remember we had 50 data sources, if one of them crashed, subsequently all other scrapers and linkers crashed. The airflow just stopped the whole pipeline, and we had no data. So if one link was weak, the whole pipeline was weak. We had unnecessary reading and writing from Postgres, and we had these single-threaded linkers. So, for me, the obvious choice what to do in this position was to analyze the airflow logs and runtimes. I started with addressing the longest-running parts of the pipeline, and I was taking them one by one and trying to replace them with something that scaled much better. In this case, the longest runnings were the linkers. They ran about 4 days, I think, each of them. So I thought, okay, so we have 70 gigabytes of data. This is bordering something that is suitable just for one machine. And I know that in the future we are going to scale with our data sources to magnitudes that will be 10 times, 100 times, maybe 1,000 times more. So I have to be prepared for the future. So I decided that we will use Apache Spark, and we will replace the linkers with Apache Spark. Who here is familiar with Apache Spark? Okay, so just to briefly introduce you what it does. It is a distributed computing engine that is a little bit similar or is following on ideas of Apache Hadoop. It distributes parallel computations into nodes. It takes data, it distributes them in the partition, and each partition is computed on a separate node. What are the benefits of it? If you design your application well, Spark can scale somewhat linearly with the amount of data you have. So this is good because once you rewrite your algorithms into Spark and the algorithms don't have high complexity, then you can scale reasonably. Also, if you want to just speed up the processing, you can just throw more machines at it and it computes faster. So we had this computing, at this time we had a cluster that took all the data from the Postgres, distributed to a cluster of machines, and started to compute. And when it was done, what happens? Each of the machines had 16 cores, and if you remember how Venkat was yesterday talking about the IOs, then you have several machines writing into one poor Postgres machine with single cores, and that wasn't good. What you do is basically distributed denial of service on your own infrastructure. So we had to address these issues. We had to address first read and also writes, because these were completely different animals. So we had linker that ran some 7 hours, and only 1 hour it was actually computing. So you are paying for your cluster, you are paying for 6 hours of 8 machines that are just sitting there and waiting for the JDBC to clean, and sometimes you have errors, it was crashing, it didn't really work. Of course, you could say, okay, why are you not scaling the Postgres? Then I would have to maintain some infrastructure of Postgres, and you have to imagine, you have to still think of what was my goal. I want to present a database that is quite small and doesn't cost much money to my ML team, and they will just run a couple queries a day. So running a cluster of Postgres would be overkill for it. However, I already had on my hand S3, which is a key value store. Are you here familiar with Amazon AWS S3? Okay. So AWS provides a key value store that automatically scales across their machine. So you don't have to maintain any infrastructure, and it can allow you to read and write in quite nice speeds. So I thought, okay, so we had this large CSV files in S3 already. Why don't we pre-process them, and why don't we reuse them when we update them just ever so often? And we can still keep the crawlers in Python, because the speed of downloading of the crawlers, it was something that Postgres was absolutely fine with dealing with. So we've done this change, and it worked very well. We basically eliminated all the read problems from the linkers part. However, we still had the write problem. And here is where some tricks from Postgres came handy. Basically, Postgres is allowing you to use query that is called copy from. Either you can copy from a binary Postgres format, or you can use copy from CSV file. What it does, Postgres is not updating any indices, and it starts a transaction, so you either insert everything at once, or it just crashes. And also, it uses it the most efficient way that it knows. So it uses all the cores possible. It optimizes the I/O. So if I want to provision such database, I will just tell it, okay, so these are the CSV files, and just use copy from these files and dump it into your database. And it worked really well. So when we outputted the data from Spark, we were no longer inserting them in Postgres, but we inserted them back into S3, which is, remember, it's a scalable storage. And out of the scalable storage, we used copy from query that at the own pace of Postgres, it inserted the data, and everyone was happy. You know, we weren't over provisioning the Spark cluster. We weren't burning any money here, and the Postgres wasn't overloaded. It was just at the right speed. But still, we had the problem where, at some point, we needed to have crawl and scrape data from the internet inserted in the Postgres. So still there was some dependency between the data in S3 and web and from the website. And we thought, okay, so we have these long-running crawlers and scrapers. What can we do about it? Why not we take every single run of it, when it finishes, output it to the S3, and then take it from the S3. And the rest of the pipeline, if at least one revision of the web scrapers and web crawlers revision is in S3, we use the latest revision available. Sometimes, you know, when it's crashing, okay, you can have something that is a month old because no one fixed it. But if there is at least one revision available in the S3, then you can continue with running your pipeline. You can spin up all these Spark machines, these Spark clusters. You can load the data from the S3. Remember, now you have also the web crawlers and web scrapers in S3. You crunch your data, you output it back to the S3, and then we run the copy from script to load the Postgres, and everyone was happy. You know, this is how it can look like. You can have several instances of crawlers and scrapers. Remember, this can be the revision from first crawler, this different color is the second crawler, etc. And you always take only the latest completed revision. And by this you can achieve decoupling of crawlers and scrapers from the rest of the pipeline. And we pushed it all together under 3 hours, which was a great success. Yeah, this is the state of the pipeline right now. We are also validating the data. Just a couple tricks what you can do with validating the data. Check generally for some empty columns and empty rows. Handpick some records that you are very familiar with. For instance, we have an array of companies that we know what are their information. We know when they were breached, someone went through the data and manually picked all the data from the data sources. And because our data sources are additive, they don't change the historical data, we can say, okay, if we are seeing this data, we know that the pipeline is somewhat safe and it has valid data. We also check for the expected cardinality. So when we are downloading the data from crawlers and scrapers, we are outputting metadata, and then we are checking every single step if somewhere the data didn't get lost. And also when the database is provisioned and is finished, then we check a delta validation between two distinctive pipeline runs. So because we know that data are getting only added, not deleted, we know that we should see at least the same data, or at least the same cardinalities of data from the previous database, from the earliest run. And we are heavily relying with validation on shapeless And if someone is familiar with Scala, with advanced Scala, then I can walk him through the code if he likes shapeless. For the future work, we want to leverage some of the new features that have been introduced in Spark 2.3 that has been released 2 weeks ago. Now Spark, because it historically until 2.3, it required to run on the ARM, on Mesos, or as a standalone. There is a new feature that allows you to deploy it on Kubernetes, which is a very strong feature that allows you to unify your infrastructure, and then you can bet everything on the Kubernetes and on Docker containers. So I can wrap all my crawlers and scrapers that are still in Python into Docker containers, and I can run it on a single Kubernetes cluster. I want to also automate the release of and spawning of the Kubernetes cluster, so it's not running all the time. So when we'll need the Kubernetes, we will just pay for the cluster, deploy everything, run it, take the database, thank you, goodbye. And we want to add more data and attach the Monte Carlo simulation at the end of the pipeline that is not done yet. What we have learned from it: don't use Postgres as an underlying data storage for Spark if you don't scale it appropriately. It's a really bad idea. Analyze your queries, because you should always pick your underlying data storage according to what are your queries and how quickly you need the data and if you need transactions, etc. So if you are like us, that you are taking all the data at once and you are basically doing no querying on it or just simple query on it, just use HDFS or S3 or Google Cloud Storage if you're on Google Cloud. Don't go first for fancy databases, because it takes you time to maintain it, and there is you spend some time basically just because of you want to use it. Also, the S3 is dirt cheap and scales surprisingly well, and as I said previously, it has zero maintenance. You can pick some formats like Parquet or OCR that even provide some primitive querying or primitive transactions. If you're not familiar with these formats, go look them up, because they are really useful. Further lessons on AWS, they are not really so positive as the slide before. The AWS pipeline that we use for provisioning the EMR cluster, it is really buggy. It has hideous interface, but it really does the job. If you're not familiar with how to spin up the EMRs, the clusters on AWS, just use their interface. But remember, once you click save, you can't change half of the values. So you have to export it to JSON file, then open it in the text editor, then change the values and upload it back, and then it works. Also, the AWS support is really rubbish. If you can do your analysis of the AWS features in advance that you need, always do it, because they are not available in all regions. So when you are going to run something that is across several regions, chances are the regions are using different encryption and they just simply don't talk to each other. It happened to us. We had to pay to report it to AWS. It's still not fixed. It's still not fixed over, how long is it? Over half year? Yeah, but I had a nice chat with people at 4 o'clock in the morning. Also, when you are using AWS EMR, throwing more resources doesn't necessarily mean instant success, because the more cores you have, the higher granularity EMR is giving you and the less memory you have. So if you have a machine that has 64 gigabytes of RAM and you have 4 cores, then you have 16 gigabytes for 1 core. But you can have instance when you have 16 cores, and you have 128 gigs of memory, and suddenly you have only 4 gigabytes per, if I'm calculating correctly. No, okay. So the higher instance configuration doesn't necessarily mean doesn't necessarily mean instance success. So watch out for the memory configuration if you will be playing with the Spark and you will have larger data sets. Also, when using AWS, there is this thing that is called spot pricing. When AWS is not using all of their machines, they are giving them for what's called spot price. You can bid for it. It usually costs much less than you would pay for it normally. But what they can do is they can take the machine at any time when they need it, or someone bid it more. In our experience, when you are running something around 1 hour, maximum 2 hours, it rarely occurs that the machines get taken from us, and we are still saving up to 75% of the cluster cost. Also, Spark can somewhat recover from taken machines as long as the data fit in the rest of the cluster. So this is a tip. Play with it, try it. It's highly recommended. You save some money. Do you have any questions?
Why do you use PostgreSQL for storing your data? What are the advantages comparing to, let's say, MariaDB?
I have personal experience with Postgres as a tool that follows ANSI SQL much better than MariaDB. Mm-hmm. And also, what we are, and this is applying to CAI, we are trying to develop a knowledge of technologies that can be shared across the company. So when we have, like right now, 5-6 startups, then we are using, if we want to use SQL database, that we go for Postgres. And we don't want to change it because we would, that we can take people from one project on the other project and they are still familiar with the technology.
And regarding your scrapers, why do you use Python? Isn't there any better solution, maybe more performance-oriented in Scala?
Yes.
Because I did some research and I'm also using Python for my scrapers. So that's why
everyone does that because you start with getting the data and you are at the moment where you are just wants to quickly something to spin up and knowing that you quickly want the data. And the crawlers and scrapers are actually something that gets they get on like a second line. And well, right now we are actually having talks about building some resilient and nicer crawlers. But if you will have any hints that we actually are talking about it right now, we were looking into Apache Notch as a crawling, but it didn't really work well for our needs because we need to query APIs, we need to scrape sites, we need to process all sorts of endpoints, and it would take a fair amount of work to replace it, and so we just left the the Python crawlers as they were.
Thank you.
Mm-hmm. Okay, if you have no further questions, let's take a short recess and we'll in 15 minutes, 10-15 minutes, we can continue with the Scala workshop. If you want to stay here for the workshop, you are more than welcome. I will guide you through with my colleague Marcel through some essential features of Scala, and at the end you will try your own first program. We will work on some fractals, so you are welcomed.